Hello everyone, this is Dr. Lennon, and today we're going to look at the chain rule. So the idea of the chain rule is pretty simple. We're trying to, again, find more classes of functions that we can take derivatives of, and one of the ways to create new functions is substituting them into other functions, i.e. composing the functions. So the idea here is how do we find, so we're finding the derivative of composed functions. So let's write down exactly how it goes. When we go through them, I'm going to write it in a slightly different way to help you organize the material. Sorry, I should have kept writing the chain rule. So what the chain rule says is we're going to suppose we have a function h of x, and h of x is formed by plugging g of x into another function f of x. Then the way you find the derivative, h prime of x, is it is exactly f prime of g of x times g prime of x. So let's look at some examples, and I'll show you how I like to set it up. And again, we're going to be appealing to a lot of the shortcut rules from the past, but again, what we're going to do is just differentiate here. So the first example, let's say f of x is the function x plus 3, or x cubed plus 1, quantity raised to the 100th power. So what I like to do is I like to think of what is the inside function or inner function, and what is the outside function? What is it being plugged into? A lot of times if you see parentheses or grouping symbols from order of operations, we know that happens first, so that's typically a common choice for the inside. So here that's going to be x cubed plus 1. And our outside I would write as t to the 100th. So if you would take your inside x cubed plus 1 and replace it where t is in parentheses, we get exactly f of x back. So then you just take the derivative of each one of these in the usual way. So we get 3x squared, the derivative of 1 is 0. The outside prime, we bring down the 100 and lower it by 1, so we get 100t raised to the 99th power. And then f prime of x is formed by essentially multiplying the bottom row here. So we're going to take 3x squared and multiply it by 100t to the 99th, but we're going to change t into the x cubed plus 1. So we have 3x squared times 100, and then change t back into x cubed plus 1. It was really just a placeholder variable for that inside function anyway. And then simplifying it, we can multiply the 100 with the 3x squared because they're not raised to something more complicated. So we get 300x squared times x cubed plus 1 raised to the 99th power. And that is how we find the derivative of part A there. Okay, let's go ahead and look at another one. Again, once you get used to the setup, these kind of get easier and easier. You just have to recognize what's being plugged in, so how to decompose the functions, and remember our shortcut rules. So here we have g of x is 9, the square root of 9 minus x squared. So here our inside function is just going to be what's inside the square root. That's how you would simplify if everything were just a number. That's what you would do first. And then the outside is the square root of t. Remember, when we're taking derivatives, often it's easier if we write that as a fractional exponent, so t to the 1/2. Okay, so to take the derivative of each one of those, the derivative of the inside prime is going to be minus 2x. The derivative of the outside is going to be 1/2 t to the minus 1/2. And then we can multiply in prime by out prime and replace t by 9 minus x squared. So here g prime of x is going to be minus 2x times 1/2, and then change t back to 9 minus x squared to the minus 1/2 power. So the 2 and the 1/2 cancel, so we can actually write this as minus x divided by the square root of 9 minus x squared. Remember, the 1/2 you can change back to a square root, and if it's a negative exponent, that means it can be written with the same positive exponent in the denominator. So that is our derivative for part B. Okay, so moving onward, let's look at, so this is one, this next one is one that you might be a little bit surprised about. So we know that if we take the derivative of the natural log of x, we get 1 over x. But what if we were taking the derivative of the natural log of 7x? You might guess, oh, it's 1 over 7x. But in fact, that's not going to be the case. So let's go ahead and see that. So here our inside function is just going to be 7x. And our outside function we can write as the natural log of t. So then the derivative of that, the derivative of the inside is 7. And the derivative of the outside would be 1 over t. So this is where the chain rule comes in. So what we have there is we have h prime of x is going to be 7 times 1 over 7x. So in fact the 7's cancel here and we get 1 over x. So we actually get the same thing as when we take the derivative of the natural log of x. So you might think of that as a little bit of a proposition. You know, it's a useful thing to remember. So suppose k is a constant. There was nothing special about the number 7. So what we could really abstract from this is if you're taking the derivative of the natural log of any constant times x, in fact that constant isn't important and you just end up with 1 over x. So you can think of that as a little thing that you can use if you see the natural log of a constant times x again. You can just write down 1 over x. And the proof would go exactly the same as the problem we just did. You would just replace 7 with k. Okay, D, let's look at f of x equals, this one's actually a quotient, 1 over the quantity x to the 4th plus 1 raised to the 3rd power. So in fact, you know, you might think, oh, let me do the quotient rule here, but it's really not necessary if we rewrite this as x to the 4th plus 1, and then instead of 3 in the denominator, we just write it as the exponent of negative 3. So sometimes with products and quotients, you can actually just rewrite them using a chain rule and avoid having to use those formulas altogether. So here the inside is going to be x to the 4th plus 1. The outside is just going to be t to the negative 3rd power. And so the derivative of the inside would be 4x cubed, whereas the derivative of the outside is going to be negative 3t, and then subtracting 1 from the exponent, we get raised to the negative 4th. So f prime of x here is going to be 4x cubed times negative 3, and then change t back into x to the 4th plus 1 to the negative 4. So we can write in the numerator negative 12x cubed multiplying 4x cubed and negative 3, and then we can put the final factor in the denominator, rewriting the exponent as positive, so x to the 4th plus 1 raised to the 4th power. So that's it for D. Okay, so let's go ahead and look at some that maybe perhaps are even a combination of things. So some examples that are perhaps a bit trickier, but will also allow us to review some product and quotient rule stuff that we've seen. So let's look at the following example. So what we want to do here is differentiate. So A, we have, let's say, f of x equals x times e to the negative x squared. Okay, so let's just note that this derivative is a combination of both the product and the chain rule. And the reason that is the case is because we have a product of a linear factor x times an exponential type thing, e to the negative x squared, and e to the negative x squared actually has a polynomial plugged into the exponent. So we're going to have a chain rule to find that derivative. So we start with the product rule. U would be x and v would be e to the minus x squared. So that means u prime is equal to 1. And then to find v prime, this is where the chain rule comes in. So we're going to have to use the chain rule to find the derivative of v prime. And again, keep in mind, a lot of times when you're taking derivatives, don't expect them to get any nicer because usually what happens is they can often become more complicated. So the derivative of v is found using the chain rule. So let's just note that. Okay, so the inside function here is going to be in the exponent. Remember, order of operations, that would be the first thing that happens. So our inside would be negative x squared, which would make our outside just e to the t. So the derivative of the inside is going to be minus 2x, whereas the derivative of the outside is going to be e to the t. So the derivative there, v prime, again, what's going on? Well, we're just multiplying minus 2x by e to the t. So actually I'll write it down here and then just copy it above. So v prime here is going to be minus 2x times e raised to the minus x squared. So that's exactly what we get here. So the rest of it is just done finishing off that product rule. So we do u prime v plus uv prime. So 1 times e to the minus x squared is just e to the minus x squared. And then we have plus x times v, u times v prime. So we have x times minus 2x e to the minus x squared. So I'm just going to write a minus here. And then it's going to be 2. The x times x is going to make it an x squared. And we have e to the minus x squared. And that is our that is the end of finding the derivative. So it might not look super pretty, but in fact we are finished. Okay, let's go ahead and look at another example. So a lot of times when we see exponential functions, they're always written in continuous form in terms of e to some power, but let's go ahead and look back at the standard form just to help us remember one of the other shortcut derivative rules. So let's say we have 10 to the 1 minus x squared. So again, the inside here is just going to be the exponent 1 minus x squared, and the outside is going to be 10 to the t power. So the derivative of the inside here is minus 2x, and the derivative of the outside, we have to remember, if you're taking the derivative of, say, b to the t power, you're just getting the natural log of the base times the exponential function all over again. So here we're going to have the natural log of 10 times 10 to the t. So then our derivative here, g prime of x, will be minus 2x times the natural log of 10 times 10 to the t. So pretty straightforward, but maybe you would have forgotten the derivative formula for the outside prime, so I wanted to remind you about that one. Okay, continuing onward, let's look at C. Let's say we have q of x is equal to the square root of e to the 3x plus x. Again, we want to think about this as e to the 3x plus x raised to the 1/2 power. So we can do the chain rule a bit easier. So our inside function is just what's inside the parentheses there, e to the 3x plus x. And the outside, we're just replacing what's in the parentheses with t, so it's t to the 1/2. The derivative of the inside, remember the derivative for e to a constant times x is just whatever that constant is times the same exponential function. So the constant in the exponent is 3, so it's going to be 3 e to the 3x, and the derivative of x is just 1. The derivative of the outside here, bring down the 1/2 and then subtract 1 from that power. So 1/2 minus 1 is negative 1/2. You can also think of this as 1 over 2 square root t if you prefer the exponent notation. So putting all that together, again, we just multiply the bottom row, in prime times out prime, and replace the occurrence of t by e to the 3x plus x in parentheses. So here q prime of x is 3e to the 3x plus 1 times 1/2, and then we're going to change that to e to the 3x plus x to the negative 1/2 power. So if you want to rewrite that using the radical notation, it can be written as 3e to the 3x plus 1 divided by 2 times the square root of e to the 3x plus x. Okay, so let's do another one. So D, we have h of x equals the quantity of 5x plus 1 to the 4th power. So here the inside function is 5 to the x plus 1, and the outside function is t to the 4th power. So the derivative of the inside function is the natural log of 5 times 5 to the x, and the derivative of the outside function is 4 times t cubed. Just the power rule, bring down the exponent and subtract by 1. So again, the derivative is pretty straightforward. We're just multiplying essentially the bottom row and changing t back to 5 to the x plus 1. So we get the natural log of 5 times 5 to the x times 4 times 5 to the x plus 1 quantity cubed. Typically when it would not be wrong to leave it like this, but usually I like to, for whatever reason, just bring my regular constants all the way in front. So I would reorder the factors in front. 4 natural log 5, 5 to the x times 5 to the x plus 1 cubed. But either one is fine. I'm just a little bit more particular about how I like to write things. So why don't I go ahead and give you well, let's go back to equations of tangent lines. We haven't done that in quite some time. So that's something that often accompanies the derivative, right? Anytime you have a derivative formula, really it's a formula that will tell you the slope of tangent lines to that function at any particular x value. So let's go ahead and look there at some examples. So let's find the equation of the tangent line to the curve at the given point. So we have y equals 1 plus 2x to the 10th, and the point is 0, 1. So basically what's going on here is we need the chain rule to compute y prime, and that's going to allow us to find the slope. Once we find the slope, 0, 1 is the y-intercept, so we'll be able to have the equation of the tangent line quite quickly. So use the chain rule to find y prime. So our inside function here is 1 plus 2x, and our outside function is t to the 10th power. So the derivative of the inside function is just 2. The derivative of the outside function is 10 times t to the 9th. So our derivative formula is actually y prime equals 2 times 10 is going to give us 20 times 1 plus 2x raised to the 9th. Okay, so we find the slope by plugging in 0 for x, because the point is 0, 0, 1. So we find the slope by plugging in x equals 0. So the slope, let's just call it m, is 20 times 1 plus 2 times 0 to the 9th. Well, that's just 1 to the 9th, so our slope is in fact just 20. We already know that 1 is the y-intercept, so the equation of the tangent line is y equals 20x plus 1. So that would be the tangent line. So let's go ahead and look at another application example. So let's go ahead and look at this following word problem. So suppose a hot cup of coffee is left on the kitchen counter if the temp in degrees Fahrenheit after T hours is given by the formula capital F of T equals 75 plus 105 times 0.62 raised to the T. Find the instantaneous rate of change after an hour and a half. Or in other words, just find F prime of T after an hour and a half. So that was a poor excuse for an H right there. Alright, so basically we're just taking the derivative and plugging in T equals 1.5 because T is representing the time in hours. So an hour and a half would not be 1 hour 30 minutes but 1.5. So again, this one actually doesn't require too much in terms of the chain rule. It's in the chain rule section, I'm not sure why, but remember the derivative of 0.62 to the T is just an exponential function with base 0.62. So that's just going to be, it's going to have an extra factor of the natural log. So F prime of T here, the derivative of 75 is 0, so that just goes away. Then we have the 105 times the natural log of 0.62 times 0.62 to the T. And we just want to plug in 1.5 for T. So we get 105 times the natural log of 0.62 times 0.62 to the 1.5. So if you go ahead and plug all this in, you get minus 24.5. And remember, with the derivative, the units are going to be the units of output variable, degrees Fahrenheit, per units of input value, which is time here measured in hours. So if we want to interpret that, we would just say after 1.5 hours, the temp of the coffee so again, this is one place rather than use negative, we can just say it's decreasing and just say it's decreasing at a rate of 24.5 degrees per hour. And that is it. So we'll stop here and we'll continue next time with implicit differentiation. Again, chain rule, pretty straightforward. Recognize what's the inside function, what's the outside function. Take the derivative of each one, multiply those together, and replace your placeholder variable with the original inside function. So I hope this was helpful. This is Dr. Lennon signing off.